There's an interesting application of integration where it can actually be used to find a one-dimensional measurement length. The original introduction to integration showed how it was used to find the two-dimensional measurement of area. And we did this by partitioning an interval and drawing a two-dimensional figure on each partition, namely a rectangle, and then summing up the areas of the rectangles, and eventually putting a limit in front of it to find the exact area of the region. In the more recent lessons, we have seen how integration can also be used to find a three-dimensional measurement through a carefully defined integrand in the form of the disk or washer method or the shell method. Likewise, through a very careful description of the situation and a carefully defined integrand, we can also find the one-dimensional measurement of length. Specifically, the length of the graph of a function on an interval. Take, for example, the portion of the curve drawn here. This being a curve, its length is difficult to measure because we have no conventional method for measuring the length of a curve. We can measure straight line segments, but curves are a bit more difficult. But since we can measure line segments accurately, and since the entire premise of an integral is to use a rough approximation on each partition and let the limit find the exact value, we're going to take that approach here and partition the interval and on each partition we are going to approximate the shape of a curve using a line segment. Each of these line segments roughly approximates the shape of the curve. They do not give exactly the shape of the curve. That is to say, on each partition, the length of the arc on that partition is not exactly the same as the length of the line segment. However, we do know from doing limits of Riemann sums that the more partitions we use, the more accurate our estimate gets, to the point where if we eventually put a limit as n approaches infinity in front of the Riemann sum, we will get the exact measurements. So what we need to do here is start by defining the length of a line segment on a partition. As we do with partitions, we label the x values involved, starting at x sub 0 and going up to the end of the interval, which would be x sub n, in this case x sub 4 for 4 partitions. On any interval, then, the length of the line segment on the ith subinterval is nothing more than the distance formula between 2 points on the coordinate plane. Every diagonal line, and we know this from dealing with the unit circle in trigonometry, every diagonal line can be broken down into a horizontal component and a vertical component. The horizontal component is nothing more than the difference in the x values, and the vertical component is nothing more than the difference in the y values. But the line segment itself and those horizontal and vertical components form a right triangle. The line segment is the hypotenuse of that triangle. So its length, by the Pythagorean theorem, would be the difference in the x values, x sub I minus x sub I minus 1 squared, plus the difference in the y values on that partition, y sub I minus y sub I minus 1 squared. And then square rooting this will give us the distance, the length of the hypotenuse of that triangle, the distance of the line segment on that subinterval. Thus, the length of the line segment would be the summation from 1 to n of each of these distances, each of the lengths of each of these line segments. So for each partition, if we perform this procedure and we add the lengths together, we will get the approximate length of the arc. Of course, if we put a limit as n approaches infinity in front of this, it can turn into an integral that will give us an exact value. But before we do that, we're missing one very important piece here. In defining the Riemann sum for area, whether it was area of underneath a single curve or area between two curves, or in defining the disk or washer or shells when we did volume, every one of those formulas naturally had a delta x in it to account for the width of the partition. This formula does not have a delta x in it that is readily apparent, and thus that delta x is supposed to turn into the dx of our integral. If we don't see a delta x here, then we're not going to have a dx when we attempt to turn this into a definite integral. So we need to do a little bit of careful manipulation of this expression. So let us start with the distance formula. The distance formula can be rewritten using a slightly different notation. In Algebra 1 classes, when you learn about the slope of a line, we see the notation delta y over delta x, where delta y represents the change in y value going from one point to another, and delta x represents the change in the x value in going from that point to the second. That is exactly what these expressions are. We can rewrite this as delta x squared plus delta y squared. Now this is a step in the right direction because we can now see that there is a delta x present in here somewhere. Our job is going to be able to get it out so that it is its own separate factor of delta x off to the side. So again, through some careful algebra, we can do this. We can factor out a delta x squared from each of these terms under the radical. Now that might sound odd at first because the delta y squared doesn't have any delta x's in it. But another way to think of factoring out is simply dividing. If I were to say, divide the delta x squared, the delta x squared by delta x squared, and I were to divide the delta y squared by delta x squared, and then balance that division with a multiplication by delta x squared. You can modify any expression by introducing a new division or any operation, as long as you balance it with the inverse operation. So I can balance this division by delta x squared of both terms with a multiplication by delta x squared. And in a set, what I'm essentially doing is factoring out a delta x squared. This turns the first fraction into a 1. The second fraction can be rewritten as delta y over delta x in parentheses, which is then squared. At this point, we can separate this into two separate radicals. At which point, the square root and the square in the delta x factor will cancel each other out and leave us with a single factor of delta x attached to this square root. Thus, the length of the arc is approximated by the sum from 1 to n of the square root of 1 plus delta y over delta x squared times delta x. And thus, when we put a limit as n approaches infinity in front of this, this now converts to an integral. When it does, the deltas, all three of them, will switch to a d. The delta x factor off to the side will switch to dx as we need for our integral. But at the same time, the delta y over delta x will become dy over dx. So we will have the definite integral from a to b of the square root of 1 plus dy dx squared delta x, or I'm sorry, dx. But dy dx is nothing more than the derivative of the function that we are finding the arc length of. So we then have the concept that f is a continuous function suppose I should say, let f be a continuous function on a to b a closed interval from a to b, and differentiable on the open interval from a to b. The length of the graph of f of x on the interval from a to b, then, is given by the definite integral from a to b of the square root of 1 plus f prime of x squared dx. it is necessary for the function to be differentiable because the integrand is based on the derivative of the function. So we need a function that is continuous, no holes, no asymptotes, no jumps. Those things would, as you would imagine, certainly interfere with finding the length of something if it has a break in the middle of it or if it goes infinitely high or infinitely low. But it must also be differentiable because the integrand that we are using is based on the derivative of the function. So, let's look at an example or two of this. Let's start with a function y equals 1/6 x cubed plus 1 over 2x on the interval from 1 to 2. Now, first thing, we need to make sure that the function is continuous on the interval given. There is a discontinuity at x equals 0. But that is not within the interval 1/2 to 2. Therefore, the function is continuous on 1/2 to 2. Now, we also need to make sure that it is differentiable on the interval. One way to answer that is to actually find the derivative, which dovetails nicely with the fact that we actually need the derivative for our integrand. So our next step is to find f prime of x, at which point it might be helpful to rewrite the second term as 1/2 times x to the negative 1. And that will give us 1/6 times 3x squared plus 1/2 times negative 1x to the negative 2, which cleans up to be 1/2 times x squared minus 1/2 times x to the negative 2. This has a discontinuity at x equals 0, and thus the derivative does not exist. The function is not differentiable at x equals 0. However, that means it is differentiable on 1/2 to 2. Thus, we can find the arc length as the definite integral from 1/2 to 2 of the square root of 1 plus f prime, which is 1/2 x squared minus 1/2 x to the negative 2 squared dx. Now, this is not going to be the easiest thing to integrate. A large part of the reason for that is this is a composition, which normally would suggest integration by substitution. However, integration by substitution requires that the derivative of the inside function be a factor in the integrand. We have no other factors in the integrand besides this square root. So integration by substitution is not going to help us, at least not at this point. We will have to rewrite the integrand into a new form. Ideally, if we can rewrite the expression under the square root as some other expression squared, then that square root would cancel with the square, and that would fix the issue of the composition largely, possibly entirely. So our goal is going to be to take the integrand and see if we can rewrite it. So I'm going to pull out just the integrand for a moment. And in order to rewrite this, we're going to have to expand this binomial. Because of the complexity of the terms involved in it, it would be very advantageous here to write the factor twice so that we can see everything involved when we are expanding it. So we have that 1 in front, which is part of this and will be figured into it, but for now, we need to expand this by doing 1/2 x squared times 1/2 x squared, which would give us 1/4 x to the 4th. We then have the outer products and the inner products, which actually are the same thing. So we're going to have 2 times the outer times the inner. So 1/2 x squared times negative 1/2 x to the negative 2. And then lastly, negative 1/2 x to the negative 2 times itself. As it turns out then, this in the middle, the x squared and the x to the negative 2 cancel each other out, and this term in the middle becomes simply negative 1/2. Now, it's important to note here that this is the expansion of this binomial squared. When we combine the constant term of the 1 with the constant term of the negative 1/2 in the middle, this entire expression under the radical becomes 1/4 x to the 4th plus 1/2 plus 1/4 x to the negative 4. This again comes from combining the constant of 1 in front that we haven't used yet with the constant term of negative 1/2 in the middle. And the end result is that we now have a positive 1/2 between these two terms. The only difference then is that this can factor almost identically to what we had at the beginning, but it has absorbed that extra plus 1 term. And because it is now a plus 1/2 in the middle, it will factor as 1/2 x squared plus 1/2 x to the negative 2. Squared, of course. So our entire integrand is now going to change to 1/2 x squared plus 1/2 x to the negative 2 squared, all underneath that square root. And now we get the desired goal of the square and the square root canceling out. Leaving us with a polynomial style integrand where the power rule can be applied to both terms. For the first term, we would have 1/2 as the coefficient times x cubed over 3. And then we would have plus 1/2 as the coefficient times x to the negative 1 over negative 1. And of course, by the fundamental theorem, we would evaluate this antiderivative at 2 and at 1/2 and subtract them. Cleaning this up a bit, this becomes x cubed over 6 minus 1 over 2x. Note that this does appear to be very similar to the original function, but it is not exactly the same. The original function was x cubed over 6 plus 1 over 2x. The algebra involved in rewriting the integrand resulted in an antiderivative that is not exactly the same as the original function. So while it is similar, it is not exactly the same. So we then have 2 cubed over 6 minus 1 over 2 times 2 minus 1/2 cubed over 6 minus 1 over 2 times 1/2. In the first bracket, this gives us 8 over 6 minus 1 over 4. In the second bracket, this gives us 1/8 divided by 6, which is 1 over 48, minus, well, the 2 times the 1/2 in the denominator is just 1. So we have 1 over 1, which is 1. This is then a matter of finding a common denominator in order to add these. So we have 64 over 48 minus 12 over 48. Distributing this negative will give us minus 1 over 48 plus 48 over 48. Adding all of these numerators then gives us 99 over 48, which can be further simplified to 33 over 16. Like the previous lessons here, this is not an intuitive answer. We have to trust the process, and that includes trusting our algebra. We can check our answer by putting the original integrand into the calculator, understanding, of course, that the graph that it produces will not look anything like what the original function would look like. The other part of that is that putting this into the calculator assumes that we wrote the correct integral to begin with. So checking your answer with the calculator is not a guarantee that you have the correct answer at the end, but at least will help you to know if you integrated correctly, if you evaluated the integral correctly that you wrote. Now, there are some cases where we may have to write the function in terms of y rather than in terms of x. We saw this with area between curves, where there were times it resulted in a simpler integrand by defining the functions in terms of y rather than x. We saw cases in the disk and washer versus the shell method, where because the nature of the formulas was different, that integrating with respect to x might have resulted in a more difficult integrand, whereas converting it to be in terms of y would result in a simpler integrand. So there are times where that becomes necessary. One of those times is when at the endpoint of the interval, the function has an undefined derivative, such as the square root function, as an example. The square root function is continuous from 0 to whatever endpoint we choose to use. However, and it is differentiable on the open interval between them. However, we have one tiny problem at x equals 0. The derivative there is undefined because as we approach this, our tangent lines turn more and more and more vertical. That's a problem because the function is not actually differentiable at one of the endpoints. We would see this when we attempted to evaluate the integral. What we would see is that at the endpoint of 0, the antiderivative would be undefined. And that's a bit of a problem. However, it is only an undefined derivative when it is done in terms of x. It is vertical, which means in terms of x, that line has an undefined slope. The derivative is undefined. But in terms of y, that would be equivalent to a horizontal line. In terms of y, the derivative of the function would be 0, not infinite. So by using the inverse, by rewriting this in terms of y rather than in terms of x, we can get around that problem. For example, suppose we have the graph of y minus 1 cubed equals x squared. Now this currently is not in terms of x or in terms of y. Currently, it is an implicit equation. That would make the graph difficult to obtain, certainly. There are graphing programs that can graph implicit equations, but the typical graphing calculator cannot. In this situation, we have a function that can be solved for y in terms of x, but can also be solved for x in terms of y. So we actually have a choice for how we're going to do this. Ultimately, though, it is going to come down to which one is going to produce the more difficult integrand. In this case, we have our option. We could do it, again, in terms of x. To do that, we would have to solve this for y, which would include doing the cube root on both sides, and then adding 1 to both sides. The problem with this is if this is our function, and we have to find its derivative, we're dealing with an index of 3. And that's not going to interact so well with the squaring and the square root that are in the arc length formula. So this is not the best way to do it. The cube root, that index, is not going to interact well. The arc length formula, again, is dependent on squaring the derivative and dealing with the square roots. Squaring and square roots do not interact cleanly with a cube root. So that's going to make our lives a little bit more difficult. On the other hand, if we were willing to do this in terms of y, all we would have to do is square root both sides. Now you might say at first, how is this any better? For two reasons. One, we do have a plus or minus to worry about, except for the fact that x is always positive on 0 to 8. Therefore, we keep the positive and drop the negative. I'm writing the positive only to emphasize it here. Now again, you might say, but how is this any better? We still have a 3 in there. but the 3 is an exponent, not an index. This will actually work out better. Exponents are easier to work with than radicals with different indices. This will actually work out more cleanly for us. So we have f of y is equal to the square root of y minus 1 cubed. We need its derivative in order to make the arc length function, the arc length integral, work. So we can rewrite this as y minus 1 to the 3 halves, and its derivative would then be 3 halves times y minus 1 to the 1 half. And that's why this is going to work better, because in finding the derivative, that 3 in the exponent is now not an issue. The arc length here then, well, we're going to need to figure out our limits of integration, because the x values, the values of the interval given are x values. So we need to find the y values that are associated with them before we can define this. We'll come back to those in a moment. For now, we can set up the integral as 1 plus 3 halves times y minus 1 to the 1 half squared dy. As for the limits of integration, when x equals 0, well, the only way to get 0 out of this is to have the base be 0. Y would have to be equal to 1 here. If x is 8, eight is a cube. Therefore, the cube root of 8 would be 2, and that means that y minus 1 to the 1 half would have to be 2. Thus, 4 is equal to y minus 1, and y has to be equal to 5 here. So our limits of integration are from y equals 1 to y equals 5. This is the integral we need to evaluate. Let's take that to the next page where we have room to work. The integral from 1 to 5 of the square root of 1 plus 3 halves times y minus 1 to the 1 half squared dy. Under the radical, we have the 1, and then we have the 3 halves and the y minus 1 to the 1 half, which gets squared. The 3 halves squared is simply 9/4. Since the y minus 1 has an exponent of 1 half on it, that cancels with the exponent of 2 and simply leaves us with y minus 1. This is now a linear expression under the radical, which is very easy to work with. Combining the constant terms of the 1 and the negative 9/4 gives us negative 5/4. And this being a linear expression, its derivative is a constant. So even though we don't have a variable factor outside of the radical, that's not an issue since the inside function is linear. We can now let u equal 9/4 y minus 5/4, so that du is equal to 9/4 dy, or 4/9 du is equal to dy. Thus, our integral can be rewritten as, keeping in mind that these limits of integration are still y values, this then gives us the square root of u times 4/9 dy. Excuse me, 4/9 du. We can bring the 4/9 out front since it is a constant multiple. We can rewrite the square root of u as u to the 1/2 so that we can use the power rule on it. And this gives us 4/9 times the antiderivative, which is 2/3 u to the 3/2, evaluated at y equals 5 and at y equals 0. Now we cannot substitute the 5 and the 0 until we return this to the original variable of y. That would be 9/4 y minus 5/4. Now this can get a bit messy, but we can clean it up a little bit by factoring out and combining some of those constant multiples. If we bring the 2/3 out in front with the 4/9, we would get 8/27. And then we would have 9/4 times 5 minus 5/4 minus 9/4 times 0 minus 5/4. This would give us 45/4 minus 5/4 minus 0 plus 5/4. Everything in the bracket then will reduce simply to 45/4, and through some basic cross simplification, we can arrive at the final answer of 10/3.